So let me emphasize that today, when I'm talking about invertible stuff, I'm talking about square matrices. They have to be square to be invertible. A is invertible if there is a matrix B and R in the N, also square, same size, such that AB and BA are both equal to the identity. Remember, this is the N by N identity matrix that has all zeros except for it's got ones on the diagonal. If A is invertible, we sometimes call it non-single. And we say a singular if it is not a matrix. And sometimes we say the inverse. We often write B as A inverse. It exists. So let me give you an example. Or non-example, perhaps. Is this matrix invertible? And how do you do it? For 2 by 2, I'm going to give you a quick and easy formula way to tell this. This one is. Does anybody see what the inverse is? That's a little tricky as well. Check this. I'll only check it one way. Technically, from our definition, you probably should check it both ways. So you should multiply the other order as well. Let's see what we get. First row, first column, 8 minus 7 is 1. Minus 4 plus 4, that is 0 here. This gives 14 minus 14 is 0. And this gives minus 7 and 8, 1. So there's your inverse right there. And that works from the other side too. Okay. Any questions? Let me point something out here. If you have A, B, C, D, and multiply by D, A, what happens when I multiply this matrix? Let's see, shall we? AD minus BC. Agree? What happens when I multiply the first row by the second column? What do I get? What do I get in the entry in the first row of the second column? It's 0, don't I? Because I get minus AB plus AB. Same thing with the second row first column. I get CD minus CD. And what do I get in the second row, second column, I get minus BC plus AD, which is the same thing. Under what conditions is that the identity matrix? What do you need to happen for this to be the identity?
AD minus BC is equal to 1.
This crap has to be 1. Everybody agree? Because we got a match here, right? So this gives me the following theorem. Take any 2 by 2 square matrix. If AD minus BC is not equal to 0, then A is vertical. And A inverse is equal to times the fraction 1 over AD minus BC. So in other words, notice you're multiplying this by this number. So this entry is D over this denominator minus B over this denominator minus C over this denominator, A over this denominator. Those are the 4 entries, right? This is a nice formula. And notice you've got big, huge problems if AD minus BC is 0. And that's why I said this. If AD minus BC equals 0, then A is not invertible. Questions? Let me make kind of a terminology note here. Here, A then how many of you ever heard the word determinant for matrix? Anybody? Yeah, perhaps a few, especially maybe the 80. What is the determinant of this matrix? It is denoted this way, that A, and it is AD minus BC. This is the crucial value that tells you whether or not the matrix is invertible. This is what a determinant is for a 2 by 2 matrix. By the way, kind of spoiler alert looking forward, that if you have any square matrix, there is a notion of determinant, but it's too complicated for me to do yet, but we're going to do that in depth later. And determinant is something for a square matrix that gives you a lot of information about it. Okay, in particular, for the 2 by 2 case, that determinant tells you that whether or not it's invertible. Okay, any questions? Okay, so here is something. Yeah, A is invertible. Then the matrix equation y'all remember us solving this? right? This is one of the kind of first things we did, we set up the augmented equation. Now, this is a little bit more specialized because I'm assuming that the matrix is square. And actually, I'm gonna go a step further than that. I'm assuming not only is the matrix square, but I'm assuming that it's invertible, right? If that is the case, then this matrix equation has a unique solution. For every B in Rn. No matter what vector B you put in here, you can solve for X. I'm gonna prove this, but this isn't really a proof, it's more of a computation, just kind of fun. Suppose we have. In fact, not only am I going to show you the solution, I'm going to show you what the solution is. Like, how will we solve that?
Besides by the inverse of A.
Fantastic. That's exactly what we want to do. These two things are the same. In fact, they're both vectors in Rn. So hit it on the left with this thing, right? So this is the identity, right? And what happens when you multiply the identity matrix times X? You get X, right? There's your solution, right? And the solution has to be unique because what this equation says is if anything works, it has to be a B. Whoops, that's a mistake. That's right. Inverse. There we go. It had to be A inverse. So this is kind of nifty. Now I'm going to tell you something, and don't let this take the wind out of your sails. But this is a crappy way to solve this problem, right? Multiplying by the inverse. And what do I mean by that? Because usually, if you're doing computational stuff, computing the inverse can be sometimes extremely tedious. And actually, it's probably about, you only take about a third of the time just row reducing the matrix. So why do I do this? Just to show off my mathematical prowess because I'm extremely bored and lonely? No, it's not just for that reason. It's also because the fact that this has a unique solution, and this is what the solution looks like, we can apply later to get some things that really do streamline for us. Okay, any questions? Now, actually, when I get to this, I've got to develop a little bit of kind of background to this, but I'm going to show you actually maybe the best way by hand to compute the inverse of the matrix. First, we have this theorem. A, B, again, with the square matrix. Oh yeah, so I'm just going to do kind of 3 points here. One, if A is invertible, so is A inverse. I bet you guys can figure this out. That is correct. The inverse of the inverse is the original matrix A. Good. Two. If A, B, both the same size square, are invertible, so is AB better one gets at this. I'll give you a hint, think about what happens with the transpose. So what this says is if A and B are both invertible, they both got inverses, then so is A times B. It's also got inverse. What is the inverse of A times B? You might want to guess. You can say inverse. It's the inverses both taken in the other order. And so this might mystify you a little bit. So I'm gonna show you why that's true. And finally, three, if A is invertible, so is a transpose. So the transpose has an inverse. Anybody want to guess what the inverse of the transpose is?
By the transpose of the inverse.
There you go. So this might seem a little bit opaque, but these are important rules that you have to know. So let me what else is true? First, we'll do a warm up. Yeah, A is invertible. A inverse is unique. What do I mean by that? Yeah. It has one solution, right? This might surprise you because I'm calling people out matrices. Give me any number, just not zero. What happens when you zero, 4, 0, 4. So this row comes this column, 0. This row comes this column. This row comes this column. This matrix squares the zero matrix. But it is itself not the zero matrix. Right? Did it matter that she picked 4? What if she picked 6? Or pi, or 8, 6, 7, 5, 3, 0, 9? It would all square to zero matrix, right? There's infinitely many solutions to this equation. So the equation x squared equals 0, infinitely many solutions. This is what makes this maybe a little bit surprising. So if you go and take a matrix and figure out the inverse, right? I gave you an example earlier in class where the 2 by 2 matrix, I multiplied by the other matrix, got the identity. That's the only solution. That's the only way you can do it. And maybe this example shows that perhaps this isn't clear. Why is it unique? Let's suppose B and C are both inverses of A. What does that mean? Well, that means that AB and BA are both the n by n identity matrix. I'll just write I, right? And it also means that AC and CA is I as well. Everybody okay with that? I claim that B and C, they have to be the same. Anybody see why? Watch, this is total slime. Correct? Now, hit this on the left and see. And what's CI? What's C times I? It's just plain C. So let's group the parentheses elsewhere. Bring the C down. What's CA? It's also fine. With IB, we'll see the leads. So any two inverses have to be exactly the same. Any questions on that? Now, is old Jim having a stroke? No, not really. I'm gonna use that right here. If A is invertible, so is A inverse. And A inverse is A. Well, for one, right? So this means that when I hit A inverse on either side by A, I get the identity, right? That's a reinterpretation, right? I'm sort of reinterpreting the classic. If I hit A inverse with A, either on the left or on the right, I get the identity. So A is equal to A inverse inverse. Because it turns A inverse into the identity. And because of my warm up, there's only one, so it is in fact equal. There's no other ambiguity. This has to be it. Okay. How about, you know what? I'm just going to get on my truck and drive. What happens when I'm on AB times B inverse A inverse? What happens first? What happens to these two B's in the middle? Turns into the identity, right? So this becomes A inverse, correct? And what happens to these two? Identity. What happens if I put B inverse A inverse on the other side? Now what happens to the A's in the middle? This is a bloodbath, isn't it, right? This is B inverse B. So when I hit AB on either side by this thing, I got the identity. That means that the inverse of AB, this thing I hit on either side, must be B inverse. Okay. And finally, this business about the transpose. This is kind of cool. That's what it means for A to be invertible, right? Anybody want to guess what next step this is? Because all I've done is written some crap with A's and A inverse, and I wanted to say something about the transpose. Any ideas on what I might do to move on with my life here? Well, let's just transpose the crap out of this, right? I mean, if these are three equal matrices, now this requires us to remember something from yesterday. What happens when I transpose two things? Do I remember that identity? Yeah, that's right. It's transposes in the other order. Do I remember that? So this is A inverse transpose, A transpose. other order, A transpose, A inverse. Everybody okay with this? Now, here's the big question. What is the transpose of the identity matrix? It is the identity matrix, because all you're doing is you're just swapping all the rows with columns. And this is actually the identity. So what you get is A inverse P, AP, is equal to I. It's AP, A inverse T. And so what this means is that certainly A transpose is invertible, because you hit it on both sides of this, you get the identity, and it means that A transpose, the inverse of it is this thing, which is A invert transpose. Any questions? Let me make a note for you here. And this is probably worth your while to know. In general, if each AI is invertible, then A1, A2, up to AK inverse. So this will be useful computation for you all. If this is AK inverse, AK minus 1 inverse, A2 inverse. So to take the inverse of a product of invertible matrices, you just take the inverses and reverse them, right? Okay. Any questions? Okay. Somebody remind me what are elementary row operations?
You swap any two rows,
It would swap, right?
you can add a multiple of any row to any other row.
Right, you take multiple any row and add it to another row. What else was there?
You can multiply a row by any.
Well, you do better than that. Anything's not zero. Right, exactly. Okay, those are our 3 row operations, right? You can swap any pair of rows. You can multiply a row by, you multiply a row by any number and add it to another row, or you can multiply a fixed row by a non-zero number. So I'm just going to do this by example. Right? Suppose I make this like this. Suppose I multiply by this matrix here. What happens when I do this? This row times this column, this row times this column, this row times. So I got to change out the top. This row times this column times this column. So I do DEF in the middle. And this row times this column A, row times this column B. What did that do?
Swap the rows.
It swapped rows 1 and 3, didn't it? And notice what happens if I swap rows 1 and 3 here? What do I get? What special matrix is it when I swap these 2 rows, 1 and 3 here? Yeah, let's do one of a similar nature here. What happens if I do? What happens if I do this? ABC. THI. EF. What happens? This matrix swap rows 2 and 3. What happens if you swap rows 2 and 3 here? You type the identity. Okay. Let's put a little twist on this. What happens if I do this matrix? 1, 2, and 0. By the way, is it clear to you all? So I swap 2 rows, I get the identity matrix here, these matrices that I multiply by. So keep that in mind. By the way, can anybody tell me what this matrix is going to do? Multiplying by that specific matrix on the left comes the one full of letters. Let's see what we get. In the top row, what's my first entry? A plus. And then B plus H, C plus 2I. Agreed? The rest of it is E, E, L, E, H, I. What did this matrix do?
It added 2 of row 3. So those first row.
Okay. Right. What's the only difference here is -2. So I take -2 times bottom at the top. Let me ask you this. In this first step, I took the top row and I added twice the bottom row to it, and everything else was focused. Agreed? How would I undo this? How could I get from here back to the original matrix?
Use the substitutions.
That's right, I can multiply this by -2 and add to this, and it will erase all the stuff up there. What do you suppose the relationship is between these 2 matrices? They are inverses. Multiply them out and see, right? This row comes, this column, you get 1, 0, -2 plus 1 is 0, 0, 1, 0. Huh. So it looks like these things can kind of undo each other, the row operation. Let me do one more like this. What happens if I have anybody tell me what's going to happen here? Can you tell me without me writing it out? What this matrix is actually going to do? Yes.
It'll add 3 R1 to R2.
Correct. What this matrix should do, these things kind of leave everything alone. This 3, 1, what it should do is add 3 times this to this. So it should be 3 times the first row plus the second. And if you go through it, A, B, C, this is 3A plus D, 3B plus E, 3C plus F, and finally G. What do you suppose the inverse of this matrix is? How would you undo it?
Negative.
All right, change that to a negative. That's exactly right. Let's do one more. This one's actually the easiest. I won't write this one out. But if not, just. What do you suppose this matrix is?
It multiplies row 2 by 47.
That is correct. Everybody agree with that? Leaves the top row alone, leaves the bottom row alone, and the second row is multiplied by a factor of 47. Basically, what we've done here, the example, admittedly, is we've basically done every row operation, right? We've done the ones where we just turned the rows on the identity matrix around, that swap rows. These ones right here that had a 2 up here or a 3 down below the diagonal. These added multiples of rows, and these right here. Notice every matrix we use, if you row reduce it, it row reduces to the identity. Everybody agree with that? All of these matrices that I used to multiply, row reduce to the identity. And so here's what I want you to take away from this. So you have matrices of this form. Now this is only 3 by 3. I can do this by any size matrix you want, but I'll do the 3 by 3. So you have one type. This is a swap. In fact, in this one, it's swapped rows 1 and 2, right? And this isn't every swap. This is just an example of one. This is 3 times top plus bottom. And varying where this goes tells you whether tells you which row multiply by to add to which row. And this is multiplies middle row by 8. For example, these are called elementary matrices. These are examples of elementary matrices. And what they do is they basically give you the elementary row operations. Hence the word elementary matrix. All row operations. On A can be written as take your matrix A, and A doesn't even have to be square. The elementary matrices have to be square, but the A does. So for example, if the first one you do is a swap, then the first one is one of these. And then maybe you do another swap, so you have a different kind of one of these. And then maybe you do a multiple of 3 times the top plus bottom, it's one of these. Every operation on A can be interpreted as all of these elementary operations sort of. So you can always, whatever you do, every time you do a row operation, you can put another matrix there to multiply it out. So let me give you, is everybody comfortable with that so far? Yeah. So let me give you a big theorem here. And this tells you if your matrix is invertible, and it can be any size theorem. And there's a bonus with this theorem, because I'm going to tell you how to figure out the inverse, which is super cool. Let A be any square matrix. A is invertible. If and only if A can be row reduced. Then by non-negative. That's it. So what does it mean to be invertible? It means you can do your row operations and you can eventually get to the identity matrix, right? Another way to put this is it has n pivots. It's a square matrix. Every column is a pivot column. All right. So that's kind of a good thing to know, that that's what it means to be invertible in a square matrix, is that every column is a pivot column. And here's the bonus. This sequence of operations turns IN to A inverse. So here's the deal. If you have an invertible matrix, you can tell if it's invertible by taking your matrix and row reducing it to the identity. Whatever sequence you use to get it to the identity, if you apply that sequence to the identity, it will give you the inverse, right? So you kind of got a mirror image thing. And actually, I can prove this without doing anything. Suppose A is an n by n invertible matrix. Suppose you do your sequence of row operations and get the identity, right? Because we said a sequence of row operations like this. A is invertible, so let's multiply on the right by A inverse. And of course, A inverse times the identity is A inverse. What does this happy couple turn into? The identity. So it's gone. It's cast. Oh, so we have EK, E2, E1 times the identity of A inverse. So that same sequence of row operations that got you the identity, that will turn the identity into A inverse. Let me give you a practical sort of example here. So is, let's see, 1, 0 minus 2, 2, 2, 3, minus 3, minus 1, 3, invertible? If so, find its inverse. Okay, here's the way I like to do this. It's the same sequence. If you can reduce this to the identity, it's the same sequence that turns the identity into the inverse, right? So let's do this. Let's make sort of a giant table. My matrix A is 1, 0, minus 2, 2, 2, 3, and minus 3, minus 1, 3. Put the identity matrix over here. I am going to try to row reduce this to the identity, and whatever I do to this, I'm going to do to the identity. So if I can get to the identity here, whatever's over here has to be the inverse. The first thing I'm going to do is I am going to take out this and this. So I'm going to multiply times minus 2, take this out. And remember, you got to do things to both sides. So times minus 2 and add, times minus 2 and add, times minus 2 and add, times minus 2 and add. 1, 0. And I'm going to multiply this by 3 and add it down here. 0 minus 1 times 3 and add is minus 3. Catch me making mistakes. I get 3, 0, 1. Well, it's already starts to look convertible to me. Now what I'm gonna do is, I'm gonna swap these two. So I'm gonna leave this one. And I'm gonna swap these two, so I'm gonna put the 027. And what comes with it, which is -210 on the bottom. And I'm gonna put this one in the middle, and I'm gonna change the sign of it as well. So that's gonna be -3, 0, -1. Agree? Now I'm gonna multiply this by -2. To take out that thing. 1, 0, -2. 0, 0, 1, 3. -3, 0, -1. Multiply by -2 and add. 0, 1, that was convenient. So -2 and add is going to be 6, -2, 4, 1, 2. And now, the last thing I have to do is I just have to take out these two stragglers here in the last column. So you're going to get 0, 0, 1, 4, 1, 2 at the bottom. I am going to multiply this by -3 and add 0, 1, 0. Let's see, times -3 and add is going to be -15. -3, -7. And finally, I'm going to take the bottom row times 2. Times 2 and add. I'm going to have 1, 0, 1, or no, 1, 0, 0. That's going to be 9 and 2 and 4. And I think that's what I got. And it is indeed. I actually checked this. Check that this here, this piece right here should be A and B. Does everybody understand how that algorithm works? All right. So here's kind of a fun one to take home. See if that was convertible and find its inverse. And you might pay attention to what the form of the inverse looks like. Okay, any questions on that? Any questions? All right, you guys put this in your pipes and smoke it. I'm gonna probably post your next quiz this afternoon. If you got any questions, continue, and I'll see you guys by Friday.